take a look at 7.6, normal distributions. Basically review of what we looked at back in chapter 4. Okay, normal distributions formalize the notion of mound-shaped histograms introduced in chapter 4. Normal distributions are widely used for two reasons. First, they provide a reasonable approximation to the distribution of many different variables, and they also play a central role in many of the inferential procedures that we will be discussing in later chapters. Okay, meaning using data that forms a normal distribution from samples to try to make sense out of what's going on for a larger population. That's what's meant by inferential. Okay, but that's later stuff. In any event, let's review normal distributions. Okay, normal distributions are continuous probability distributions that are bell-shaped and symmetric, as shown in the figure below. Normal distributions are sometimes referred to as normal curves. Okay, so here's the general shape of a normal distribution. It would be centered about its average mean value mu. And let's see, there are many different normal distributions. They are distinguished from one another by their mean mu, that's where they're centered, and their standard deviation sigma. The mean mu of a normal distribution describes where the corresponding curve is centered. The standard deviation sigma describes how much the curve spreads out around that center. As with all continuous probability distributions, the total area under any normal curve is equal to 1, representing 100% of the data. Three normal distributions are shown in figure 7.18. Notice that the smaller the standard deviation, the taller and narrower the corresponding curve is. So that would be the one in the middle. Okay, that one's centered at 40. And it's got a relatively small standard deviation of 2.5. The orange one to the left is centered at 10, and it has twice the spread of 5 as the previous one. You can notice that from left to right, indeed, it's more spread out than the first one, okay, but it's not nearly as tall as a result, okay? So the narrower the standard deviation, the taller the graph tends to be, okay? So remember that the areas, picking up right here, remember that the areas under a continuous probability distribution curve represent probabilities. So when the standard deviation is small, a larger area is concentrated near the center of the curve. This means that the chance of observing a value near the mean is much greater because mu is at the center. So again, just kind of looking at these three examples, you can see they each have different centers, and they each have slightly different standard deviations. The larger the standard deviation, the shorter the curve. The smaller the standard deviation, the taller the curve. Okay. In any event, the vast majority of data always lie pretty close to the mean. And again, the comment they were making before was that if the standard deviation is smaller, you get a larger concentration of data near the mean. Okay, so again, that's the normal, that's the shape. And what do we do with these things? Well, we look at z-scores and we compute probabilities. Okay, so let's recall a standard z-score is the number of standard deviations away from the mean a particular data value lies under a normal distribution. Okay, and the formula we saw earlier in the course was z equals, I was writing it as x sub I minus mu over sigma, which just means our actual data value, data point, minus the mean divided by the standard deviation. Okay, so that's how we compute a z-score. Okay, so let's take a look at an example. Suppose newborn baby weights form a normal distribution with a mean of 7 pounds and a standard deviation of 1 pound. Find the z-score for a baby born weighing the following things. So looking at part A, if the baby was actually 8 pounds, how many standard deviations above the mean is that? So look, we're going to go z equals the actual is 8 minus the average, mu, which was 7, divided by the standard deviation they gave us, which was 1. So here we end up with 1 over 1, which equals 1. Okay, a baby weighing 8 pounds is exactly 1 standard deviation above the average weight. That's all that means. Okay, for part B, 6 pounds, the z-score would be actual 6 minus average divided by standard deviation. Here we get back a z-score of -1. That just means that a baby that was born weighing 6 pounds is 1 standard deviation below the average weight. Okay, looking at part C, a baby born weighing 5.4 pounds. And here we end up with -1.6 over 1, which just ends up being -1.6. So they're a little more than 1.5 standard deviations below the average weight. They're 1.6 standard deviations below the average weight. Okay, for part D, the z-score would be 9.3 minus the average of 7 over 1, which gives us 2.3. Okay, so a baby born weighing 9.3 pounds is considerably above average, 2.3 standard deviations above the mean. In part E, what about a baby born weighing 7 pounds? Our weight minus average over standard deviation, well, that comes back 0. So a z-score of 0 means that that was equal to the mean value. Okay, a baby that weighed 7 pounds was exactly average weight. Okay, so those are the z-scores. And then what we also look at are p-values. Okay, and again, I'm going to do this with the calculator. You can probably find these graphing calculator utilities for free online now. Or you're going to have to refer to the z-tables and notes we used back in chapter 4. Okay, so be careful here. Let me know if you have questions though. P-values. Okay, so z-scores are the number of standard deviations a particular value lies above or below the mean. P-values give the percentage of data values that lie within a certain region under a normal distribution curve. Okay, so this is the actual percentages of data that are going to lie in certain regions. Remember that for continuous data, percentages and probabilities are found by looking at the area under the curve specific to the region we're talking about. So again, to review the way we find these percentage values on the calculator, we go to second vars number 2, normal CDF, where we enter a lower, upper, mean, and standard deviation. And for the percentile values, we go into second vars, and then it's number 3, the inverse norm, where they're going to ask for the area, which is your percentile. They're going to ask you for the mean, and again, they're going to ask you for the standard deviation. Okay, so let's go through these examples, and again, if you need to refer to your z-tables and notes from chapter 4, please do so. Okay, using the newborn baby weight data. So again, mu was 7 pounds, here sigma was 1. Okay, find the percentage of babies who are born weighing less than 6 pounds. So again, I tend to like to draw the normal curve. It's centered at 7. What percentage of babies would be born weighing less than 6 pounds? So there's 6, and I'm going to shade to the left. Okay, so in terms of our normal CDF, okay, lower, in theory, these go back to -infinity and up to +infinity. So I'm not shading from like 6 to 0. I'm shading from 6 back to -infinity. And so we use -10 to the 99th power to approximate -infinity on our calculators. Upper is where we're shading up to, and that's the number 6 here. Average was 7 and sigma was 1. Okay, so when we calculate that, you should get a p-value pretty close to 0.1587. Just a little less than 16% of newborn babies would weigh less than 6 pounds. Okay. Part B, what percentage of babies weigh more than 9 pounds? Okay, so here's my normal distribution curve, again centered at 7. Here I'm looking for the percentage that weigh more than 9 pounds. So 9 is up here, and I'm shading to the right. So our lower value this time is 9, and we're going up to +infinity. So we'll use 10 to the 99th for that. Mu is still 7, and sigma is still 1. And when you go through and calculate, you should get a pretty small percentage here, a little more than 2%. Again, I'm just rounding to 4 places here. Okay. If you're using the Z tables, you should get values that are close to these, but probably not exact. All right. In part C, find the probability. So just notice a slightly different way of asking. Up here, we wanted the percentage of babies. Here, we're looking for the probability that a randomly selected newborn weighs between 6.5 and 7.5 pounds. Same idea. We're still finding the percentage of data. Okay. So here's our curve. And I want the percentage between 6.5 and 7.5. And I would expect that to be a decent size since it's pretty close to the mean here, but let's see. Okay, so here our lower value is 6.5, our upper is 7.5. Mu is still 7, sigma is still 1. When we calculate that, I'm getting just under 40%. Rounding to 4 places, 0.3829, 38 and change percent. Okay. What newborn weight would be heavier than 95% of all other newborn baby weights? Okay, so here we're actually looking for the weight that would be heavier than 95% of other weights. So this is centered at 7, and I'm looking for some number up here, I'll call it X, that's greater than 95% of the rest of the weights. In other words, I'm looking for the value at the 95th percentile. This is where we use the inverse norm feature. Okay, and so let's see, area refers to the percentile value. Make sure you do it as a decimal, 0.95. Okay, mu is still 7, sigma is still 1. Some of you may need to put it in the parentheses like this, the way your calculators are formatted. Okay, but that's the idea. And if you punch that in, I'm getting an X value pretty close to 8.64 pounds. And again, I just chose to round 2 places here. And then for part E, similar type of problem. What do the lightest 10% of babies weigh in under? So here's our normal distribution. Again, we're looking for the X value that basically cuts off the 10th percentile. What do the lightest 10% of babies weigh in under? Okay, so we want the 10th percentile value. So here we're looking at an area of 0.10 and same mu and sigma. Okay, and here I got that X would have to be under, I wrote it as less than or equal to 5.72 pounds. Okay, the lightest babies weigh in under 5.72 pounds. All right, folks, if you have any questions, please let me know. And this pretty much wraps up chapter 7. Have a good day.